Sure, thanks. My eyes are fading. I can use these. You know, I can love these. My eyes are faded. Mine's too small. It's easy to choose.
Ed, you want copies of the slides? You want
Sure.
copies of the slides?
Yeah, they have, look, they're an extra copy.
They're all yours.
You're the chair, right? Okay. Okay, so it is a great pleasure to introduce Elizabeth Chen, who will try very hard to defend her thesis today in front of you guys, and then a very vicious committee afterwards. This is a very important work, I think, in terms of the physics, but also very important for us, for our group, and the effort that we started in 1990 in testing for time reversal symmetry breaking in unconventional superconductors. The main reason, as you will see, is that the measurements that were done on some particular materials in which multiple effects occur, but only the right effects, quote unquote, right effects, show the sign of time reversal symmetry breaking as expected, or which is to us it's been an extremely important thing. So Elizabeth started working with Jing, the former graduate student who constructed this new version of the Sagnac interferometer. This was many years ago. I think what was it, in the late 20s or late 30s?
18th century, yeah.
18th century, something like that. Jing left the first year in the summer to go to China, and like any other person from China, hoped to get the visa in 1 week. He got the visa after 1 month, which allowed Elizabeth to collect enough data already in her first year, which was extremely important, that later she was giving an invited talk at the subsequent March meeting. Then she worked very hard, probably harder than anybody, on rebuilding a Sagnac system. That's the system that she's going to talk about in a helium-3 cryostat, which is a non-trivial thing, and understanding every bits and piece of that. And I think for that she's probably going to thank the group of Marty Fair quite a bit. It worked, and then the data started to come out, and the recent work that she's going to tell us about allowed for another invited talk at another March meeting this year, which at least in my group and a few groups that I know, I don't know of many graduate students that give 2 invited talks in their time as a graduate student in March meetings. So that's pretty good. So I think I'll stop here, because otherwise there will not be enough time for the committee afterwards to do their job. So Elizabeth.
All right. Thank you for that introduction, Aaron. And it's really nice to see so many people here, so thanks for coming. Hopefully you all get at least a little bit out of this talk. So my hope today is to give you basically a broad overview of what I've been working on as my thesis project over many, many years. So to do that, I just want to start by at least outlining what the problem is that we're trying to solve. So tell you something about unconventional superconductivity, some of the open issues there, and why time reversal symmetry is something that you might be interested in looking for in these materials. From there, I'll tell you a little bit about the experimental apparatus, so this wonderful, wonderful machine that I've spent a very long time trying to get to work. And then I'll go into a couple of concrete examples of what we're able to do with this kind of experiment, and some of the problems that we've been looking at and solving, or just making ourselves more confused, as the case may be. Okay, so the materials that I'm going to be talking about today are all superconductors. As many of you know, these materials have been around since 1911. The first material discovered to superconduct was mercury. And they have two defining characteristics. The first, probably the more common one that people know, is that these are perfect conductors under some temperature called Tc, or their transition temperature. But another key feature of them is that they have complete expulsion of magnetic fields. So once you go below the transition temperature, you also find that these materials will expel whatever magnetic field you've applied to them. And these two things in combination really tell you that you're dealing with some sort of electronic phase that is fundamentally different from what you've seen in, for instance, metals or insulators or semiconductors. So of course the big challenge was to understand why these materials do what they do. And so there the great triumph came in 1957 with the development of the so-called BCS theory, which explained very well the low temperature properties and superconducting transition temperatures and so forth of the known materials. So this is just a nice little plot of the highest Tc materials as a function of time, because of course you might think that some of these might be useful someday, in which case you'd want them to work at ever higher temperatures. And as a fun fact, Ted Jabal's first paper in superconductivity that I could find was the discovery of niobium-3 tin, right here. Okay, so let me just outline really quickly what I mean, or sort of the main concepts in BCS theory. So the things that I would hope that you can keep in mind for this talk are the following. The first is what we're dealing with, instead of electrons that are all sort of in a free-for-all, we're talking about pairs of electrons. So we're always dealing with sort of two at a time. And this may seem not too interesting, except that from a quantum mechanical standpoint, this fundamentally changes the statistics of the particles. So instead of not being able to occupy the same state, they can all now condense into a single macroscopic quantum ground state, it's usually called psi. And so the quantum ground state has some sort of magnitude, and it also has a phase. So those are two characteristic values with this sort of thing. And the other thing that we like to talk about is that the formation of a superconducting condensate is characterized by the opening of an energy gap. And in the BCS, the conventional BCS theory, the energy gap is isotropic, so it doesn't matter which way you look in the crystal, the energy gap is the same. And you can think of the energy gap as basically being how much energy you need to put into the system to break the Cooper pairs apart, so to destroy superconductivity. It turns out that this gap is going to be proportional to this wave function psi. And to bring it one step further, because I'm going to be using this terminology a lot, both the gap and the pair wave function are also often referred to as the order parameter for superconductivity. And this goes back to Ginzburg-Landau theory. Those of you who don't know about that, don't worry. It's basically a phenomenological way to approach this kind of problem that basically ignores all of the sort of microscopic details of what might be going on in these systems. The main idea is that you have some sort of parameter that's identically zero above the transition temperature and then becomes non-zero below the transition temperature. So in the case of superconductivity, this quantity is the gap, and moreover, the gap contains some information about the superconducting state. So this was all looking very good. So we had a really successful theory. It explained everything that you could hope to a theory to explain in these materials, and things were going along very nicely until maybe the late 70s. And so there was the discovery of cerium copper-2 silicon-2, uranium beryllium-13 shortly thereafter, and uranium platinum-3. And as you can see, they're not particularly impressive in terms of transition temperature. That's, you're not going to break any records there. But what was interesting were some of their other behaviors. So one of the first things that came up with these materials is that it was found that the charge carriers, the electrons in these materials, are actually very strongly correlated to one another. So they basically act as if they're much heavier than they are, in sort of a bare sense. And the reason that this is surprising is that BCS theory was sort of predicated on the idea that the interactions between these electrons are somewhat weak. So the fact that here the electrons are interacting very strongly with one another is a surprise. The second surprise is that if you measure some quantities, for instance, the low temperature specific heat, their functional form started to deviate from the predictions that you put forth in BCS theory. So this was, again, another thing that was starting to indicate that there was a little more to superconductors than what we understood so far. But perhaps the most striking example that there was really more to be learned about superconductors really came from uranium-platinum-3. And I've shown the phase diagram here. This really changed the way that you would want to think about superconductors. So what I'm showing is a phase diagram as a function of temperature and applied magnetic field. These data points are all indicators of thermodynamic phase transitions, one way or another. The point is that there's not just one superconducting phase, but three. So at low fields, there's a high temperature A phase, a low temperature B phase, and then at finite fields, there's the C phase. And the thing that's really remarkable about this is that if you go back to just conventional BCS theory, there's only one way to write down a BCS superconductor. In other words, all of the symmetries of the lattice are retained. The only symmetry that's broken is the gauge that sets this phase. So the fact that you have more than one phase separated by phase transitions means that at least two of these three phases have to break some additional symmetries than just the ones done in an S-wave conventional superconductor. So no matter what else you might try to argue about functional forms and the like, this is really a very stark demonstration that you can have different forms of superconductivity. And then a question from ever since has been, how do you understand a material like this? Especially in the fact that really, since that time, most of the superconductors that we've discovered have turned out to be unconventional in one way or another. And that includes the high TC cuprates, which everyone, especially in this department, really loves to study. Okay, so the question is, all right, so if UPT3 and if many of these other materials are not conventional superconductors, then how do we go about understanding them or even thinking about them? So again, we basically have to go back to the drawing board. So the underlying microscopic pairing mechanism is unknown. We don't know why these things are forming pairs and becoming superconducting. However, you can still go back to sort of a more macroscopic approach, this sort of Ginzburg-Landau picture, where you're, instead of thinking about how do you actually get pairs, you just say, okay, well, suppose we have some way of making these electrons pair, then how do we figure out what else is going on to get just a general order parameter? So how do we figure out at least what the gap is? Okay, so there's few possibilities, well, there are many possibilities for what the gap function could be. In a BCS superconductor, as I very briefly mentioned, the gap is isotropic, so it's basically the same everywhere. But there are other possibilities, such as this D-wave guy here. So anyway, so in terms of symmetries, you can consider, of course, gauge symmetry, which will be broken in any superconductor. But there could be symmetries that are broken in addition to this. So one example is spatial symmetries. So for instance, in this one, you have directions along which the superconducting gap goes to 0. So you basically don't have a superconductor. These are known as nodes here. And you can have an inversion in the sign of the wave function. So these are all just generally known as the nodal structure. You can also consider the dispersion, so how quickly the gap grows around a node. That's a slightly more subtle point. You can also look at parity. So if your crystal has inversion symmetry, you can split everything up and think of these materials in the spin sector as being either singlet or triplet. Sorry for the jargon. It's just another way to categorize these materials. But another symmetry that you can consider, and it's a very fundamental one, is time reversal symmetry. And so this one may not be as obvious just from looking at pictures like this, but I would like to argue that it's one that we should be looking at. So maybe first I should just tell you what time reversal symmetry is. So basically what we're thinking about is what happens if you send t to minus t in some way. So it's like if you're looking at a video of a system and then you play it backwards, are the laws of physics the same, roughly speaking? So this may seem kind of abstract, but there's actually a lot of classical examples and things that we encounter all the time for which time reversal symmetry is considered to be broken. So the easiest example, perhaps, is just magnetism. So you may remember from college physics or high school physics that if you have a charged particle that's moving around in a circle, it'll generate a magnetic field. But if you then reverse time, so you have the same charged particle is now going to go around in the opposite direction, so the magnetic field is going to point in the opposite way. So in this sense, we say that the magnetic field breaks time reversal. In other words, the B field is not equal to its time-reversed partner. And the same thing turns out to be true if you look quantum mechanically. So generally, magnetized materials, materials with magnetic moments, that sort of thing, those are all said to break time reversal symmetry. So in the specific context of superconductors, though, what I'm considering are electrons that are, again, appearing in these Cooper pairs. And mostly what I'm going to be talking about are pairs that have some net angular momentum, sometimes called an orbital magnetic moment. So you can think of these as having, some sort of orbital angular momentum, maybe positive in one direction. If you reverse time, you can almost think of them as rotating the opposite way, and now the angular momentum is going to be flipped. So these are not the same. And for those of you who would rather see maybe something a little more concrete, you could consider just maybe the simplest example would be so-called P plus IP pairing. So this is for LZ equals plus or minus 1. Your actual wave function would look something like this. So it has a spatial orbital part as well as a spin. This is spin triplet. And if you apply time reversal, you find that basically this I goes to minus I, so the orbital part is not the same. The spin, if you reverse the spins, the spin state isn't really changed. So that's the main difference. It's just that this state is not equal to this. And that's, in that way, we say that it breaks time reversal. Okay, so if that didn't make sense, don't worry. The point is an unconventional superconducting state may or may not break time reversal symmetry. And it's an important distinction, as I hope to convince you in the next slides. Okay, but so for now, if we just assume or hope that time reversal symmetry is something that we might want to look at in some of these exotic materials, the next question is, how do we actually detect such a state experimentally? And this turns out to be a non-trivial problem, but we're able to approach it by exploiting magneto-optical effects. Okay, so it may seem a little, it probably doesn't seem that odd actually, to try to use polarized light to look for time reversal symmetry breaking. The way I like to think about it, at least in a hand-wavy sense, is if you consider, say, right-handed circularly polarized light that's heading towards a sample and left-handed circularly polarized light that's heading away from the sample, those two states are related by time reversal. And so you can imagine that if time reversal is broken in your sample, it should have some effect on what happens to circularly polarized light upon reflection. So that's sort of the general concept. And what I'm talking about specifically is going to be called the polar Kerr effect. And that idea is you just take linearly polarized light and shine it on a sample that, say, has a net magnetic moment in the z direction. The linearly polarized state, of course, is an equal superposition of right and left circular polarizations. So then upon reflection, if this material breaks time reversal symmetry, then you'll in general have an unequal superposition of right and left circular polarized states. So your outgoing polarization is now generally going to be elliptically polarized, and the major axis of the ellipse is going to be rotated relative to the incoming beam by some angle known as the Kerr angle or theta k. So the nice thing is this is a quantity that is identically zero if time reversal symmetry, well, generally is zero if time reversal symmetry is preserved, and it departs from zero if time reversal symmetry is broken. And again, you can be more quantitative about this. You can relate the Kerr angle to the complex indices of refraction in the material. Basically, at the end of the day, it comes out to be related to the off-diagonal component of the conductivity tensor. And for those of you who like thinking about symmetry properties of the conductivity tensor, you'll again notice that this particular term is going to be non-zero if time reversal is broken. Okay, so far this sounds really good. So we have a quantity that departs from zero if time reversal is broken. So we're ready to go measure some stuff. The only problem is that for superconductors, this angle is very, very small. So to give you an idea, if we were to do this kind of experiment and looked at something like iron, then the rotation you get is about 10 milliradians, which is about half a degree. For superconductors, however, the estimate is that the kind of rotations you'd be looking at are on the order of 1 microradian or less. And to give you an idea of what that would be, if you were to, say, have the center of a circle at this corner of the room and look at something happening like the edge of the circle is on the other end of the room, then a microradian of rotation is equivalent to a displacement of, I don't know, a few microns, something like that. So it's really quite small, but it's still non-zero, but it's really quite small. So suffice it to say that we can't really do this using just crossed polarizers, unfortunately. We do have a number of experimental requirements in order to be able to resolve a signal like this. The first is we really need to, as much as possible, reject any other effects that may look like this kind of rotation. So specifically, linear birefringence is a problem for us, for those of you who know what that is. Another thing that I haven't stressed so far is that, again, we're doing a measurement of sort of a magnetic effect, but it's in a superconductor, which of course expels magnetic fields. So typically, you might try to enhance the resolution of your signal by applying some bias field. We can't do that in this case. So we need to just have basically an absolute measurement. And finally, it needs to be quite sensitive. So on the order of tens of nanoradians, ideally, and over a wide temperature range, depending on the material that we're looking at. All right, so that was the challenge that we set off with a while ago. And the approach is to use an interferometric technique to try to resolve these very small phase shifts. And the basic geometry is called the Sagnac loop. This has been used for a very long time for a number of very interesting applications. But the basic idea is you have some path that sends light around in a loop. You have an incoming beam that you split, and you send half of it around one direction and half in the other direction. And then you look at what happens at the output. So as it stands with this figure, of course, if you just send the light around and recombine it at the end, you just get the same waveform out that you put in. In other words, these two counterpropagating paths are not phase shifted from one another. But one easy way to break the symmetry in this system, and actually it breaks time reversal in the system, is to imagine putting this whole thing on a turntable. So if you're just turning this loop around while you're also doing this experiment, you'll notice that since the speed of light has to be constant, what happens is that one path, actually the light has to travel further than the other while going through the instrument. And what that means in the output is that now there's going to be a phase shift between the two beams. And it's going to be related to the rotational speed of the loop. So this is actually one of the original uses for this kind of design. It's in gyroscopes and that sort of thing, and it's still used today. But what I'm interested in is using this kind of apparatus to look at magnetic materials. So again, we can think of rotation as a way of breaking time reversal symmetry, but another way we can break time reversal symmetry is by inserting a magnetic material. So that's what we could do here. There's some details with whether you use linearly polarized light and the like. But just supposing that you send some light through in this direction, it would pick up a rotation of a certain angle. The other direction would be minus that. So the overall phase shift in the end would be twice, what's called the Faraday angle. So that would be in transmission, apologize. It's basically related to the magnetization of the sample. Okay, so then the next step is to think that, well, in the end, of course, I've been telling you about polar Kerr effect and how great that is in reflection. And you'll notice that we can actually use this to look at a material in reflection by noticing that there's a symmetry in this system. So you can imagine drawing a line through this diagram here, and if you could somehow fold the interferometer in half, you'd basically be measuring a material in reflection, and all you need is a way to independently route these two beams of light through your system. And so that was the big breakthrough that really Jing worked on. And it led to the final design that I used, which is sketched with many components here. But the basic idea is the same as what I've been showing you. So the main part of the interferometer really exists over here. And what happens is we're able to use something called polarization maintaining fiber. which is basically your usual fiber optic cable where light is transmitted in the core, but there are also these stress rods on either side, which basically act to change the index of refraction in this direction versus in this direction. So those are called the fast and the slow axes of the fiber. It basically means that you have two channels with which you can route light through the system. And so what this looks like in terms of counterpropagating paths is you can imagine having half of your light going through, starting, say, in the fast axis. It goes through a quarter wave plate, gets turned into, say, right circularly polarized light, bounces off the sample, gets rotated again through the quarter wave plate, and returns through the slow axis. And then the other path would start its life in the slow axis, go through the quarter wave plate 2 times, and return through the fast axis. So those are our 2 loops. The nice thing about it is now, of course, the area of the loop is 0, which means that you don't have to worry about things like the rotation of the Earth and other such effects that were so great for gyroscopes, but not so great if we're just looking at magneto-optical effects. So there's a second piece. So that's sort of the main idea behind the interferometer. The second piece is that we have what's called an electro-optic phase modulator that's also in the system. Basically what that does is it is able to wiggle the phase of the beam that's going through it that happens to be vertically polarized. So it's basically a way of shaking the loop at different times in its path. We end up with a more complicated interference pattern, but we're able to pick out specific harmonics of the modulation frequency using, say, a lock-in amplifier, and that actually really improves the resolution of the system. So if you have it set up right, which is a big if, you can actually back out the Kerr angle just by looking at the voltage that you read on a lock-in that's tuned to the modulation frequency, and then divide by the second harmonic voltage that you read out. All right, so that's sort of the basic idea of what we're trying to do here. Just so for everyone who's paying attention to the materials and quantities that we're looking at, just to sort of run through. So the wavelength of the light that we're using here is 1550 nanometers, which is about 0.8 eV. It just happens to be a convenient wavelength to use because it's a telecommunications wavelength. So we have a lot of very high quality and relatively affordable parts. That's really all there is to that. The spot size that I'm using is mostly around 10.6 microns, although one thing that I changed with this particular design is it's possible to adjust this. I never actually took advantage of that, though. The incident power is typically around 10 to 20 microwatts. And it's important to keep this as low as possible because, again, we're eventually going to be dealing with systems that are very, very cold at helium-3 temperatures or so, and sample heating becomes significant at that point. Okay, and then the other figures are just that it's relatively stable over the course of the time that you want to do a measurement. It's relatively quiet. In other words, you can integrate for sort of a human length of time and get reasonable statistics. And it's relatively stable in terms of temperature. So this is something that we can actually use, thankfully. And the last thing I want to go into before getting into the actual data is just to tell you generically what you would expect to find if you were to do a measurement using this kind of interferometer. So a really nice example was done by my predecessor, Jing. So this is using a Sagnac interferometer to look at just a ferromagnet. This is strontium ruthenate 113, and it has an ordering temperature of 150 Kelvin. So what happens if you put this material into your interferometer and cool it down a whole bunch of times is you get traces that are sort of like this. So this is a Kerr angle going up to, say, 15 microradians, function of temperature. So of course, as I mentioned earlier, ferromagnetic ordering is something that breaks time reversal symmetry. So this is reflected, no pun intended, in the data here as the fact that a Kerr effect onsets at the ordering temperature of 150 degrees, and it saturates along with the magnetic moment as you head to lower temperatures. So that's the first point. The second point, as you have undoubtedly noticed, is that if you cool this thing down a whole bunch of times in zero fields, you get a whole range of values for the Kerr angle, and the sign also changes. And this can be understood by just recalling the fact that generally these kinds of materials, if you cool them in zero field, they will form domains. So there will be some alignment in one part of the material, and then a neighboring one may be aligned. I would have to check that. Okay, so I wanted to point out that, that there's antiferromagnetic order at about 5 Kelvin. It has a very small moment, nonetheless, and some people will argue that it may not actually be an intrinsic feature of the system, but it's something that we'll have to think about, at least as we consider what happens at lower temperatures. But in the end, what we want to really look at is the superconducting state. And again, mostly I'm going to be thinking about what's happening at zero field. And we have the A phase, which onsets at what's called Tc plus, or 550 millikelvin. And then the B phase is now at Tc minus, or around 480 millikelvin. That's a bit higher than what's shown in this graph, because this was from 1990. Since then, sample quality's really improved, so these temperatures are a little bit higher. Right. So I thought I should talk a little bit more about what the actual strategy is in terms of classifying superconducting states and all the possibilities. So the basic idea, so please don't be afraid of this. So the basic idea here is that we want to basically figure out what all of the possible order parameters could be for this material and figure out what their symmetries are. Then you can do measurements to test whether various symmetries exist or don't, and basically cross off items from your list. So what we start off with is the fact that we know what the crystal structure is. It's hexagonal. So there are going to be a number of symmetries just by the fact that the electrons live on this crystal lattice. So there's various rotations, there are mirror symmetries in various planes, there's also inversion symmetry. And what you can do now is think about all of the possible basically subgroups of symmetries that may exist. So if the idea is if you're breaking some symmetries of the crystal but not others, how do you characterize that? And that's going to involve the sort of full force of representation theory, which I'm not going to get into. The point is that you can do this, and you can very easily categorize all of the possible ways that you can have broken symmetry and something with this crystal symmetry. And you can also write down some example functions that might describe your wave function in the end. And so that's somewhat helpfully listed here. And now we can go through and see what other experiments have done to try to narrow down the possibilities from this infinitely large list. So the first is, at least some people are interpreting NMR night shift to mean that the material is a pseudo-spin triplet. In other words, it's odd parity. There's some argument about this, which I'm not going to go into. But if you want to believe this, then that crosses off basically everything in this even parity column. And then you can do any number of measurements to try to get at the nodal structure of the material, which again, I'm not going to go through. But again, these basically tell you that some of these proposals are going to be favored and others are going to be eliminated based on what you see in terms of where these things go to zero, how many zeros there are, that sort of thing. Right. So one that's been particularly important for us is this Josephson interferometry experiment. That one would show that there's line nodes at 45 degrees in the A phase that go to an isotropic B phase, which turns out to be, I think, compatible with either E2G or E2U. That's just the notation. But anyway, I'll get into that in a minute. And again, so just to fill out the list, there's also time reversal symmetry. And again, it isn't obvious where that comes in here, but where it does appear is the fact that you have some possible representations for which you have a two-dimensional basis. So in other words, you need two sets of functions in order to fully describe the system. And it turns out that the coefficients of these can have some relative phase. So in other words, you could have kx plus iky, something like that. And if you have this imaginary component, you will get broken time reversal symmetry. So that is something that's sort of implicit in these systems as a possibility, and it's something we want to look for. Okay, so most of the previous measurements have been sort of coalescing around this E2U theory, which I thought I should spend a little more time talking about to let you know what it is that we're looking at. So again, the idea is we have a whole lot of possibilities allowed by the symmetry of the crystal lattice. We're trying to narrow them down. And the model that was starting to float to the surface is this so-called E2U1. And what you end up with in terms of the gap is sort of illustrated schematically here. This sphere in the middle is supposed to be the Fermi surface, for those of you who care about such things. But the idea is you basically can describe the gap, or you can describe the pair wave function with this somewhat complicated expression that has two coefficients called eta 1 and eta 2, again, because it's a two-dimensional representation. And the idea is in the A phase, this eta 2 is equal to 0, so you can forget about that. And if you just look at this top part here, you'll see that, well, if you want to plot this, then you'll see that it has has fourfold rotational symmetry, so it'll have two line nodes in the basal plane. Then if you go into the B phase, what happens is that eta 2 comes in, and it is imaginary. And so again, if you want to do a little bit of mental math, you can see that you can actually factor this expression if eta 1 is 1 and eta 2 is I. And you'll find that the magnitude now is going to be constant as as a function of momentum. So in other words, spatially speaking, the B phase is going to be isotropic, but because of the fact that there's this imaginary component, it's also going to break time reversal symmetry. So that's really great. There are a lot of experiments that support this kind of picture. One of them that I happen to like for a number of reasons are measurements done by Josephson interferometry that show the presence of these 45-degree line nodes and the isotropic B phase. But that's not the only picture out there. And there are other experiments that are interpreted in the guise of other interpretations. So one example that's been quite recent is some thermal conductivity measurements, which seem to show that there's twofold rotational symmetry in the A phase and then an isotropic B phase, which may not seem like a huge difference at first, but there is an important difference in that the E2U picture here has a B phase that breaks time reversal. In this picture, the B phase does not break time reversal. And the fact is that, a partisan of either of these could argue that, that they have support from time reversal in the sense that the people who tried to look for time reversal symmetry breaking by MUSR, there was one group that said time reversal symmetry is broken, and there was another group that said that it isn't. So, in other words, the previous attempts to resolve this question were inconclusive. So this was a really good candidate for a technique like ours to go in and see if there's something we can do to resolve this question. So that's what we're trying to do. Can we observe broken time reversal symmetry, specifically in the B phase of uranium-platinum-3? So what we're doing here is we first had to find a really good crystal because, of course, you want to make sure that you're looking at something that really reflects the physics of the system as opposed to just some weird impurity that happened to be in your growth chamber. So anyway, so we were very fortunate to be able to work with the group of Bill Halperin at Northwestern University, who has these really beautiful, very large, high-quality crystals of uranium-platinum-3 that we were able to use. This really is a dream come true for someone who has to do these kinds of measurements and align things by hand under a 10-micron beam. Nick looks skeptical. But anyway, the idea is we now mount this into our interferometer such that the C-axis is oriented up. This is the direction we want to test. And there are a few things that we need to do. So the first, of course, is to measure Kerr effect and see if it is indeed reflective of broken time reversal symmetry, as we'd hope. But there are a few other things that we need to check. The first is that we need to verify that whatever signal we see at low temperature is not related to the antiferromagnetism that we saw earlier. And I'll talk more about this in just a minute. The second thing, of course, that we want to know is, does whatever Kerr effect we see coincide with actually the lower transition temperature rather than the upper one? And they're relatively close, so this is something that we really need to be careful about. So in order to try to tease these two temperatures apart, we also measure mutual inductance, which is basically you wind a coil around your whole sample, You use that to apply a small magnetic field, an AC magnetic field, and then you measure the response of the sample with some inner counterwound coils. The idea being that once the material goes superconducting, it will start to try to expel the fields that you're applying to it. That can be picked up here, and so that will be a good way to identify TC just in the bulk. Okay, so moving through our list, the first thing again is to think about antiferromagnetism. So as I said before, there may be a small antiferromagnetic moment. So this was some neutron scattering data showing the onset of this order at about 5 Kelvin. And what we see if we look at Kerr effect, this is just a blow up here, is really not a whole lot. So this is 100 nanoradians is about the size of this here. And the different colors are basically just different field cooling conditions. But the point is that as far as we can tell, there's nothing going on in terms of Kerr effect as you go through the antiferromagnetic transition. So the important thing is just to say that even if antiferromagnetism does break time reversal symmetry, it doesn't seem to directly affect Kerr effect as far as we can tell. Again, this isn't a huge surprise. So first of all, antiferromagnetism has moments that are aligned opposite to one another, and we should be sensitive to some net moment developing in the material. Moreover, the moments lie in the plane, in the AB plane of the material, and we should be sensitive to moments that are in the C, along the C axis. Nevertheless, this was an important thing to check. People would be angry with us if we didn't, so there it is. So we can now confidently go to lower temperatures and see what else there is to see in this material. So again, the first thing is to look for superconductivity in general, which is going to tell us TC+. And that's going to rely on using our mutual inductance little setup here. And this is what you get as a function of temperature. So basically what we do is we identify TC+ with the onset of Miser's signal, which is basically where your mutual inductance, or the real part, is going to start deviating from basically your linear normal state background. So it's right about here, which is right about 550 millikelvin, as we would hope. That said, one thing that I mentioned a little bit, but really we do have to be careful about, is the fact that even though I'm measuring mutual inductance over this whole crystal here, when we measure Kerr effect, we're actually looking at a much smaller area that's sitting right under an optical beam. So it's possible that there can be heating caused by the beam, in which case we have to worry about whether there's going to be some shift in the temperature in the signals that we see. So we can actually see this, this effect of sample heating even in the mutual inductance data. So basically I can do this measurement with the light off and then with the light on, different powers, that sort of thing. And we can actually see this curve move. So the amount of depression caused by sample heating is just shown by this gray bar here. So in the bulk, at least, it's about 8 millikelvin. And compared to that, at any rate, in the superconducting A phase, if we look at just the Kerr effect data, there again isn't a whole lot going on. So we're not able to see anything so far. But what's really striking is that as you go to still lower temperatures, now you get a pretty clear departure from the background of the Kerr angle. So that seems to be maybe around 450, something like that. It's hard to tell based on the size of the error bars here. And again, we want to take sample heating into account. There are a few ways to do this. It's hard to do it experimentally. So what I've also done is done some simulations. So at any rate, the worst the sample heating could be is basically indicated by this rather thick gray bar here. But the point is, even taking that into account, there's a clear separation between the Kerr effect transition temperature and TC+. And since there aren't any other phase transitions going on in this region, we really have not much choice but to identify the onset of Kerr effect with the onset of B phase superconductivity at TC-. So this is all looking very promising. But there are a couple other things that we should check. So again, we should really make sure that what we're seeing is consistent with time reversal symmetry breaking. And one of the key indicators is the response to a magnetic field, as I outlined earlier. So this is the experiment that I did. The zero field data from the previous slide is plotted here in gray. And the red data is what happens if I do the same experiment, except I've cooled the sample down in a small positive field, turn the field off at base temperature, and this is what I get when I measure upon warm-up. And then the blue is if I do the same thing, but I cool in a small negative field and look at what's left over as I warm up in zero field. So a few things that we can note here. One is that the field-cooled signal is, well, first of all, we can basically orient the sign of the Kerr effect using a small magnetic field. This is, again, as we would hope to be the case if this is coming from what we think it's coming from. In addition, you can draw a couple of conclusions from the fact that the field-cooled signal is the same size as the zero field-cooled signal. So one thing we can say is, or one thing you might be concerned about, is whenever you have a superconductor in an external field, you have the risk of nucleating vortices. So vortices are trapped magnetic flux. Those can persist even if you turn the field off. And of course, if you have trapped magnetic flux, that may give rise to a Kerr effect as well. So the fact that the field-cooled signal looks the same as the zero field-cooled signal suggests that we're not seeing a vortex effect. That would usually manifest itself as some additional piece here. And then the second thing that's sort of interesting to note is that the zero field-cooled signal is the same size as the field-cooled signal. And so what I mean by that is if you think back to an earlier slide where I was talking about domain formation, you would normally expect that in zero field, whatever Kerr effect you see would be sort of random in sign and random in magnitude. And that actually wasn't what we observed. Basically, all of the zero field measurements were the same size. Most of them were the same sign, which is sort of interesting. What it suggests is that the domains, if they're being formed, are very large. That actually turns out to be consistent with other people, with what other people have measured using crystals from the same group. So it's not entirely outlandish. All right, so that brings me to the end of our first series of experiments. So let me just again wrap up what I've tried to go through here. So the first thing, of course, is that we have Kerr effect that appears below about 460 millikelvin, which is well separated from the A phase superconducting transition at around 550 millikelvin. The maximum signal is quite small, about 400 nanoradians, but it's within the order of magnitude estimate that we have, that we can do for this sort of material. We've done some, I've taken sample heating and power dependence into account. So we can't account for the separation between these two transitions by optical heating. Moreover, the chirality or the sign of the signal can be trained with a magnetic field, and it doesn't appear to be coming from trapped flux. So all of these things together suggest that time reversal symmetry is broken, for one, and for two, that the time reversal symmetry breaking happens in the B phase and not in the A phase. So this is consistent with our E2U picture and several others, but really the main conclusion is that of broken time reversal symmetry. There is a second part of this that I didn't want to get into because I was afraid I wouldn't have time. But I thought I should at least mention that you can look at the temperature dependence of this kind of signal. It's a little hard to do great fits because the error bars are so large. But the point is that there are people who have thought about how you actually get a Kerr effect and what the temperature dependence of such an effect should be. And at the very least, what we have so far is consistent with the picture that's come out of a couple of groups wherein the Kerr angle goes as the product of the real and imaginary components of the gap function. So again, yeah?
And how do those depend on temperature?
Oh, as the square root of 1 minus t over tc squared. That was what we were using for our fit.
Not the 1 over times. But there are two transitions here.
Right. Yeah, so the idea is that, well, I could show this. So the idea is that that this is basically only valid below the second transition temperature, if that makes sense. So, right. So this is what we were using. The fact that this doesn't work above Tc minus. But once you
Right.
go below TC minus, then you have a piece that presumably came on at TC plus, another piece that came on at TC minus. And it makes a curve that looks kind of like this, which, you know, it's not inconsistent.
Wait,
How about
where's
that?
TC minus?
It's around here, somewhere in the range of 450 to 500 millikelvin.
And you know that in this sample that the resistive transition is at the higher temperature.
That's right. Well, we did mutual inductance because this is a really good metal and resistance is hard to measure.
Uh-huh.
Good measure.
I mean,
But yeah,
does
also
it-
Bill's group
it-
measured it.
You know, this is a completely sensible theoretical expression to fit it to. The thing that the data looks more like, that it looks like it rises linearly with T minus TC below the lower transition temperature.
Yeah. No, I don't disagree.
Okay, they are too close, the two TCs are so close to each other, I don't think you can tell. The arrow bars.
So,
Oh, sorry. I just realized.
yeah, I mean, I guess one could hope, what happens with pressure or something like that to those TCs?
That's a good question. I don't know off the top of my head what the pressure dependence is.
But if you do enough, I mean, if you go to your measurements with magnetic field,
Uh-huh.
for sure, they're just before that.
Yeah.
And if you collect enough data, then, I mean, you see that it's consistent with that, and that's the simplest form that you expect.
Maybe. Anyway, we can discuss this more. My point was just that, insofar as there is some theory about how you get Kerr effect out of an
No, I
uncontrolled,
understand
you
the
know.
theory,
Yeah, okay.
The curve makes perfect sense
Okay,
theoretically.
okay.
That's why I'm suspicious of it.
Okay, well,
In principle, you should be able to do things, like if you could take difference curves between curves done, say, under strain and without strain or something like that. You could take a derivative of the curve with respect to TC. Then having it be linear from one temperature, the derivative would just have a discontinuity, whereas with the other form, it would have a divergence. So,
I see.
I don't
No.
think the data right now is good enough.
No,
I understand.
sadly, I did my best, but
couldn't you have fudged it a bit?
I don't know. But that was the best I could do. All right, well, so that's why this is with an asterisk. But the main conclusion, I think, can still stand. So I realize that I want to keep this within time. But the last thing I wanted to talk about, and I'll try to do this quickly, is about the second system that I looked at, and that's uranium, ruthenium 2, silicon 2. And this also happens to be a very old and very interesting material. It was discovered not long after uranium platinum 3, but also the same year as the first high TC cuprate. And so there, of course, has been a division of attention in the superconducting community ever since then. But what's very interesting about uranium, ruthenium 2, silicon 2, again, is it has a very unique phase diagram. And I've shown it here. This one is a function of pressure, so I happen to know the pressure one for this, and temperature. And what's remarkable about it is the fact that at about 17.5 Kelvin, you see a thermodynamic phase transition, so there's a discontinuity in specific heat. You can see it in resistivity as well. So you know that there's a phase transition here, and you should associate with that some sort of broken symmetry. But so far, the broken symmetry hasn't been identified. So we don't know what the ordered state is. Hence, this is called the hidden order state. And then within that hidden order state, there is also small superconducting region below about 1.5 Kelvin. It's believed to be unconventional, but it's not as well studied because, this has really perhaps attracted the most attention for people studying this material. Nevertheless, the superconducting and hidden order phases may be related. This phase appears to live entirely inside of the hidden order. They're both quenched by pressure and turn into just a large moment antiferromagnet. So I think there are reasons why you might want to study the superconducting state. You could potentially also learn something about the hidden order by doing this.
Wait, Elizabeth?
Yes,
You have the black line is the superconducting,
this guy?
yeah.
Yes.
And is that data, does that come down and hit zero at the antiferromagnetic boundary, or does it run into the antiferromagnetic boundary?
I think, so I think there's some argument about this. So there's a question, I don't think that the transition temperature, that it runs into the antiferromagnetic boundary, but there's some debate as to whether TC becomes zero exactly where the nail temperature becomes zero, or if this dome actually sort of dies off before then.
I missed
There are
what the
triangles
4-degree
to the right there.
transition is.
I'm sorry?
The open circles, what are they?
Oh, I think, so these were resistivity measurements. I think they were trying to look for something that was like superconducting fluctuations. So yeah, so this is not a phase transition, but otherwise this was the best data-driven phase diagram I could find. Okay, so my particular reason for being interested in this particular material, despite the fact that it has this very confounding high temperature phase, is the fact that there's at least some work that suggests that time reversal symmetries should be broken in uranium, ruthenium-2, silicon-2. The work on the nodal structure has led to a sort of cartoon picture of the gap that's like this. It has point lobes and the like. So this at least would be consistent with some interpretation where the gap is so-called D-wave, so L equals 2 for those of you who like that. Anyway, it's kz, kx plus or minus iky, which, as you may recognize by now, is something that should break time reversal. Another interesting thing that's come up out of the sort of vacuum of understanding of what's going on in the hidden order is that there are a lot of very interesting proposals out there that try to accommodate both superconductivity and the hidden order in this system. And you end up with some very exotic topological type states with very interesting spin textures that I am not going to try to explain. But the point is that a number of these proposals also believe that you should have broken time reversal symmetry, and that you may have more than one angular momentum state that could be involved in superconductivity. So sort of that's what I knew about the system. Some questions we might be interested in looking at are things like, well, what symmetries are broken in the hidden order? Might time reversal be one of them? And then we actually have a concrete thing that we can test in the superconducting state to see if that is indeed chiral. And another thing you might want to know is if the broken symmetries that are seen or not are intrinsic to these states, or if actually we're not looking at something that tells us about the fundamental physics of the system, but rather is just an impurity kind of effect. So what we see in the hidden order, again at around 17.5 Kelvin, is, okay, there's a small field trainable signal that we're able to see here. This is resistivity data from the same crystal, so we know where the hidden order transition is. So, at first we thought, okay, this is a case of time reversal symmetry breaking, but it turns out that the picture is a lot more complicated than that. So another thing that we tried to do, since we're dealing with a high temperature phase and we don't have to worry about vortices and the like, is that you can try cooling down the material in larger and larger fields. So this is at 2 Tesla going down to 100 Gauss, and then -1 or -2 Tesla. And there are a few things that are striking about this. The first is that the size of the Kerr signal seems to depend on the size of the field that you use to train it, which is certainly not what you would expect, at least in our very simple picture of time reversal symmetry breaking states that we look at with this kind of technique. The second thing that I like to point out is, again, it becomes clear when you look at this high field data that the Kerr angle doesn't decay to 0 until well above the hidden order temperature. So around maybe 25 Kelvin or so. So we're not able to very simply relate what we see here to the hidden order. So we're not sure that what we're looking at has anything to do with hidden order at all, in fact. Nevertheless, other people have seen some interesting things starting at 25 Kelvin, so there's certainly a lot more work to be done there.
Are those measurements made in zero